Hello and welcome back to another electricity and magnetism extra practice video. Today we will be covering the superposition of electric fields, and as always, the information and questions used are from the Essential Calculus-Based Physics Study Guide Workbook, Volume 2 by Chris McMullen. When finding the superposition of an electric field, you will have two or more charged points, and more often than not will be asked to find the effect of the net field strength at a certain distance between both of them. You will use the standard electric force equation as well as the electric field equation, but also the angle equation, which is the inverse tan of the change in y and the change in x. Some other important information to know. Coulomb's constant has a value of 8.99 times 10 to the 9th, but in this video I will be using 9. The elementary charge of a proton or electron is 1.6 times 10 to the negative 9th coulombs. Like charges repel and opposites attract. And the distance formula, which is the square root of the change of x squared plus the change of y squared. A monkey-shaped earring with a charge of 6 microcoulombs lies at a point 0, 2 meters. A banana-shaped earring with a charge of negative 6 microcoulombs lies at a point 0, negative 2 meters. Your goal is to find the magnitude of the electric field at a point 2 meters, 0. Sketch the electric field vectors created by the charge at the point 2 meters, 0. Label the electric field 1 and 2, as well as their angles, theta 1 and theta 2, with the angles being counterclockwise from the x-axis. To start, we have to note that the first point, this point, I will be using as E1, and this point down here as E2. To start, note that I will be using this point as point 1, and this point as point 2. For point 1, the charge is positive, and for point 2, the charge is negative. Therefore, the electric field from point 1 at this point will originate from the point with the highest electric potential to the point of the lowest electric potential, resulting in the vector to look like this. However, for the other point, because it's negative, it has a lower electric potential, resulting in this vector coming from the point of interest to point 2. So with that we have E1 and E2. Now, because x positive is going to be over here, we have to go all the way around to get this theta. For this one, we will also go all the way around to get this angle. Note which quadrant that the angles are in. This one is in quadrant 4, while this one is in quadrant 3. Apply the distance formula to determine R1 and R2. Alright, remember that the distance formula R is equal to the square root of the changes in x squared plus the change in y squared. Let's start with 1. We have, for Rx, we have our initial and our final. So we will have 2 minus 0, square that, and then 0 minus 2, and square that. We end up with 4 plus 4, which gets us 8. And then we have to maintain the square root throughout. Here we have the square root of 8, which can be rewritten as 2 times the square root of 2. And now for our second one, we will have the star being the initial and the second point being the final. So we have 0 minus negative 2, square that, plus 2 minus 0 and the square root of that. We end up with 2. This ends up being 2 squared, which gets us 4. And this also ends up as 2 squared, which ends up 4. Root of that, we get 8, square root of 8. And what do you know? R2 is also 2 times the square root of 2. Now we need to use trig to find the reference angles for each field vector. Let's take a look at R1 to start off with. So we know that the vector is going to look like this. And since we're using this angle here as our reference angle, we know that opposite is going to be sine, and the adjacent is going to be cosine. And then for R2, we will be using this as our reference angle, meaning that this will be our opposite, and this will be our adjacent. You could also rewrite R2 like this, and use this as your angle of reference, and you would end up with a very similar sine and cosine as with R1. Determine theta 1 and theta 2 with the information from parts A and C. Well, since we know the let's take a look at R1 first. Since we know that this is going to be our sine and this is our cosine, we are going to then use our angle equation, being our incident angle is going to be equal to the inverse tan of the changes in y over the change in x. Since we know our change in y is 2 and our change in x is also 2, we know that we are going to be plugging in tan of -1 of 1, which makes sure your calculator is set in degree mode, which gets us 45 degrees. And now when we look for angle 2, using this as our reference angle, we get the very similar sine and cosine, and we get that the change in y is 2, while the change in x is also 2, and therefore our tan, which is 1, so we plug this into our inverse tan and also get 45 degrees. Alright, determine the magnitudes of E1 and E2. Alright, in order to determine the magnitudes, we are going to be using the equation E is equal to K, the absolute value of the charge, divided by the distance squared. We will use this equation because we have our charge and the distances that we have solved for in part B. So for E1, we will be using 9 times 10 to the 9th, and then the absolute value of 6 times 10 to the negative 6 because of the microcoulombs, and divide that by 2 square root of 2 squared. Now when you square this, it instead becomes 4 times 2, which then is 8. We know that our 10s are going to combine to get a resultant 10 to the 3rd. If you look up here, we see that we have 6 and 8, which both can be reduced to 3 and 4. For the sake of simplicity, you multiply them together, 9 and 3 together, you get 27, divided by 4 times 10 to the 3rd. If you were to plug this into your calculator, you would get that the resulting magnitude is 6,750 newtons over coulombs. And because we know that E2 has the same distance as E1 and the same absolute value for the charge, we also know that E2 will also have a magnitude of 6,750 newtons over coulombs. Now we have to determine the x and y of each magnitude. For example, if we look at our first vector, we have that our angle, which is 45 degrees, and our magnitude of 6,750 newtons over coulombs. We have our angle of reference, which makes it this is sine and this is cosine. And in order to get our components, we have to multiply the magnitude of the vector by the trig of the angle that we're finding. So in this case, in order to find the x, we need to multiply this by sine of 45 degrees. In order to find the y, we have to multiply the magnitude by the cosine of 45 degrees. According to the unit circle, we know that 45 degrees is a point where the values for the x and y are the same, both of them being the square root of 2 over 2, which results in both of these amounting to the same magnitude of for their answer. Since we know that the sine of 45 is the same as the square root of 2 over 2, we multiply the magnitude of the vector by that instead. Which will end up with us having 3,705 times the square root of 2 for our x component of the first one. Note that this will be positive because from our angle of reference, the x is moving towards the right, which is the positive direction. When we multiply for our y, when we multiply the magnitude by a cosine of 45 degrees, it is also the square root of 2 divided by 2, which will yield us the same magnitude of 3,375 times the square root of 2. However, this one will be negative because from our reference angle, the vector is moving down, which is our negative direction. The same can be said for, or something similar can be said for our second angle, or for our second vector. Using this as our angle of reference, we know that this is sine, cosine. We know that our angle for the second one is also 45 degrees, while our magnitude is also 6,750. Now, the equations are similar to where we multiply the magnitude by the sine or cosine of the angle, which yields us a similar expression to our first vector. The only differences in this case will be the direction in which the vector components are going. Both of them are negative in this case, as the x is moving left, which is our negative direction, and the y is moving down, which is our negative direction as well. Determine the components of the resultant vector. Essentially, in order to get the e of x, we will be adding e of x from the first vector with the e of x from our second vector. We know that from our first vector, it has a value of 3,375, and it is positive because the x from the first vector is positive, while the x component from our second vector is instead negative because it is moving left. This results in our x component of the net vector to be 0. Alright, by contrast, we have for our e to the y to be the sum of the y component of our first vector plus the y component from our second vector. We know that both of these are negative 3,375 radical 2 because they are both moving. Both of these components are moving downwards. This results in the net y component being negative 6,750 radical 2. And because this is still a component of the electric field, the units are still newtons per coulomb. Determine the magnitude of the net electric field point at 2 meters 0. Now, in order to get the resultant magnitude, we have to use the Pythagorean theorem to where e squared will be equal to the y component squared plus the x component squared. This can be seen here in the Pythagorean theorem, this can be seen in the Pythagorean theorem as a squared plus b squared is equal to c squared. For this, we will take the square root of the sum of 0 squared because our x component was 0, and 6,750 radical 2 squared, as this was our y component. We end up with it being the square root of 6,702 radical 2 squared, this square root, and the radical or opposing operations in a sense to the point where they cancel out. So we get our resulting vector being 6,750 radical 2. Do not forget that this is a magnitude, so the sign of the value doesn't matter because it's absolute. Determine the direction of the net electric field at point 2 meters 0. Once again, in order to find our angle, we have to take the inverse tan of the change in y over the change in x. The change in y in this case will just be our y component divided by our x component. So the issue here is that it will be undefined because our e of x is equal to 0. However, we do have an angle for our net charge because of the graph over here. We can see that our horizontals will cancel out. resulting in only the y components to be relevant, meaning that because both y components are, in a sense, straight down, and the x component has no factor because they canceled out, that means that our angle theta is going to be 270 degrees, which is 3/4 of the circle, going past 90, 180, straight down, 270. Thank you for watching.